All right. So we have an exam on Wednesday of next week. So hopefully you're well ahead of that and already have started preparing. So we're kind of at the point in the acid-base stuff where titrations are complicated, but only in they're kind of a summary of everything that you've learned. So it's sort of, they're complicated in the sense that they're sort of cumulative for the acid-base chapter. But once you sort of understand how to solve all the different problems in the acid-base problem chapter prior to titrations, they're not super intimidating. It's really just a matter of knowing what to do, like which problem-solving approach to use at which point. And I think the GChem website for UT, we have links to on the UT homepage, the campus homepage, does an excellent job. It has a ton of really good resources for kind of understanding titration. So anyway, so in the last class, we looked at a situation where you have like a strong acid and you're titrating it. Or it's being titrated by a strong base. And those problems are reasonably straightforward as far as titrations go. It's just part one of these is you work at like a neutralization. And then part two is, well, I guess if I would say part one is convert everything to moles. Typically, you're, for the types of questions where they're asking for pH along a titration curve, you convert to moles. Two is calculate excess acid base. And then three is convert back to concentration. So really, these are just neutralization problems. You just have to be careful that when you're working on sort of the neutralization part, you want to be working in moles. And then when you're trying to calculate pH, you want to be working in concentration units, because pH is ultimately in concentration units. But reactions, when we think about them, or the way chemists usually think about them, is in terms of molar ratios. So you want to be in moles, not in volumes or molarities. Okay. So you can summarize what's going on in a titration curve using graphs, that sort of makes things a little bit easier. So if you have if you're doing a strong acid, so you're titrating a experimental setup is strong base in your burette. And you've got a strong acid down here. You can make these plots where you plot pH, how the pH changes, as a function of how much base you add. So you're adding in base from this burette, drop, 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 into the acid. And you have some way of monitoring the pH of this solution. So you have some sort of pH probe in here, and you're looking at how the pH changes as a function of strong base that's added. And what you'll see is what you would expect. So in the beginning, you have a strong acid, and so your pH is going to be very low. And then sort of the rest of the curve is, you know, I don't know, not super easy to predict, but it takes on this sigmoidal kind of function. Where it sort of starts out and looks kind of linear almost, you know, like it's a gentle rise, the pH changes pretty slowly. But then as you approach pH 7, use a different color for that too. Let's say right about here where you're at pH 7. You see that the pH starts to change like super rapidly, and then it just starts to level off once you get past that. So before this, like at this part of the curve, so you're adding in base. So as I add in base with the acid, I'm going to consume the acid and just make water. That's essentially what's happening here. So if I'm looking at something like HCl and I'm adding it in sodium hydroxide, I'm going to make water and sodium chloride. So I'm neutralizing the acid with every addition of strong base. And then, so in the beginning, I have an acidic solution. It's just pure acid. That's where I'm at right here. And then as I add base, the pH rises because it gets less and less acidic. So I'm adding more base, it's less and less and less and less acidic, until I get here where I'm exactly equal in terms of acid and base. And this is the equivalence point. So for a strong acid, strong base reaction, the pH is just equal to 7. And now when I get to the other side, I have no acid left in the flask. So it's as if on this upper part up here, where everything is basic, so I'm basic right here, it's as if I'm just titrating in base into pure water. So here I still have some acid left. Then I hit the equivalence point where I have half of each. And then after that, it's just getting more and more basic. So I'm not even doing any neutralization reaction once I'm up above pH 7. Right, I'm just adding in more strong base. So you're just making a more and more concentrated solution of pure base there. So the titration curve is nice because it just kind of it neatly summarizes everything for titration. What you want to be able to do is, if you go back and look at the previous lecture, you want to be able to like talk about it in terms of volume. So typically the way the problems come up for this is we'll say, you know, you're given a certain amount of strong acid and you're asked to, and a certain amount of volume of sodium hydroxide is added and you're asked to calculate the pH at that particular point. And so for these, it's reasonably straightforward. You just sort of use this workflow here. So things get more complicated when we move on to weak acids and weak bases. And the main thing, there's a bunch of things that are confusing, but the main thing is, let's take a look at So this is a strong acid, strong base. Let's look at weak acid titrated with a strong base. Yeah, so we've got a weak acid titrated with a strong base. And so we can start out kind of just doing comparison of the pH curve. So again, you start out, you're doing the same plot. You're plotting pH as a function of milliliters of sodium hydroxide that we've added. And you're starting out at a very low pH down here, somewhere around 0. And the curve is going to take a similar shape. It's going to be sigmoidal. So a sigmoid looks like this. You know, it kind of looks exponential in the beginning, and then it levels off. I mean, for an exam, no, you won't have weak acid, weak base. We'll do weak acid to strong base, weak base, strong acid. Weak acid, weak base problems get kind of complicated. But yeah, so we have this sigmoid, which more or less looks a lot like if you look at the population, not the logarithm of it, but if you just look at the population of people who have coronavirus and sort of how it grows exponentially, and then there's a lockdown or something, or I guess ideally we haven't reached that point, but you know, there's some herd immunity or something, but there's an inflection point here where you're like, things start to level off. And so these types of shapes describe lots of phenomena. Let's take a look here. So the thing about this, the thing that separates the weak acid, weak base titrations is that the equivalence point, which is always kind of in the middle of this, it's always kind of in the middle of this vertical part of the titration curve. It comes at a pH that's not 7. So let's just say, I'm just making up, you know, whatever the acid and base is here. But let's just say that it comes right here. So at the equivalence points, the pH is higher than 7 for when you titrate a weak acid with a strong base. So your acid and base at the equivalence point, moles of acid. How do I want to say this? Actually, let me come back to that. So anyway, so that part should feel like kind of weird. So at the equivalence point where you have equal moles of acid and base, your pH is not 7.
Is this like specific for like weak acid, strong base, or would this be the same for like weak base, strong acid?
It'd be the same. That's a good question. So the question would be, the question was, would this be the same for weak base, strong acid? And the answer is sort of. For a strong, we can look at one of those titration curves as well. But for a weak base, strong acid, the curve looks like this. So it's sort of inverted. So in that case, everything is opposite. So so you start out at a high pH, and then you go down to a low pH, and instead of your equivalence point coming above 7, it comes in below 7. I can just draw one of those right now, and we can look at all three and compare them. this is weak acid, strong base. If we look at so now we're looking at weak base, titrated with a strong acid. So you also notice that like the thing that I'm titrating, so I never use a weak base or a weak acid as the thing in the burette, right? The thing that's being titrated is always the weak acid or the weak base. So maybe you'd have like milliliters of HCl or something down here. That's sort of an unrealistic looking function there. And I really want to get, so the equivalence point would be like right there. I don't know that I'm doing a good job of, let me try again. Trying to keep it to scale with the other one. There we go. It's like my shitty art skills combined with trying to draw on the iPad just doesn't work out very well for me. There we go, close enough. So here, you start out basic, and then you pass through the equivalence point, and then things become acidic again. So here at the equivalence point, our pH though is going to be somewhere around 6. So you can see that for a weak base titrated with a strong acid, the equivalence point has a pH that's lower than 7. And so when we compare this to what I wanted to do. Strong acid, strong base. And then we can look similarly for a strong base being titrated with a strong acid. So these titration curves at the bottom, we're dealing with strong and strong. The equivalence point is always 7. The equivalence point is always 7. When you're dealing with these other situations where you have a weak acid, so if you're titrating a weak acid, or a weak base, there your equivalence point comes out to not be 7. The other kind of useful thing, or the other kind of interesting point on the titration curve, especially for weak acid, weak base. Let me get a new color here. Is these half equivalency points? So these are points where you're exactly half. I think they call them the half equivalence point, but you're halfway. You're halfway to the equivalence point. So that means that the amount of weak acid you have is exactly equal to the amount of weak base, like its conjugate base that's formed in solution. And so this is where the pH is going to be equal to the pK of the acid, or in here, in this case, the pH will be equal to Well, I guess it'd still be equal to the pKa. Depends on what you're trying to calculate. But so in both these cases, the pH is equal to the pK at the halfway to the equivalence point. So this would be where B minus is equal to pH. And this follows out of the Henderson-Hasselbach equation, which is just that the pH is equal to the negative log. Sorry, the pH is equal to the pKa plus the log of, in this case, B minus over BH. So when BH, if this is true, B minus equals BH, then log B minus over BH is going to be log of 1. And so that's why the pH ends up equal to pKa. So this is a very useful experiment. So if you have if you have an acid, for example, and you don't know what its equilibrium constant is, this is the experimental setup for calculating, or an experimental setup for kind of figuring out what its equilibrium constant is. So you can figure out the pK of the acid by doing a titration. You get this kind of curve out of it, and then you know that the halfway point here is going to be where the pH is equal to the pKa. And so you can kind of experimentally derive what the association constant is for, or dissociation constant is for a particular acid. So what makes these things? Yeah, the thing that's added is, I think usually the experimental setup for this is that the thing, you can do it any way you want, like, a titration is a titration, but usually the way it goes is that the strong acid or the strong base is inside the burette. So the thing that you're titrating is the weak acid or the weak base. So if you look at the plots for titration curves, either here or on the GChem website or something, you'll notice that on the bottom here, it's always a strong acid or a strong base. It's not like some universal truth about titrations, but it's just for GChem, this is kind of how it's always done. So you're adding in your strong base, you're adding in your strong acid to a flask of your weak acid or your weak base. Okay, so if you look at the last, I posted some problem solving videos on YouTube. If you look at the last, I think it's the last video on there. Hopefully I arranged them chronologically. But if you look at the last video on there, it's a neutralization problem, but it takes you more or less through all the different parts of the titration curve. And so they have some really nice worksheets on the GChem website if you go to the titration section, where it sort of tells you how to work things out. So if we look at, let's just focus on a weak acid. The calculations are all very similar for weak acid, weak base. So if we look at a weak acid and we titrate it with a strong base, we just looked at this, you get a curve that looks something like this. And then you'll have the equivalence point will be here. Which is where the pH is equal to 8. Usually you're titrating with sodium hydroxide or some sort of strong base, but and it walks you through, so different parts of this pH titration curve. So you can think about it like this, like in terms of setup, you can say, like, a pretty common way to ask these questions is, what's the pH? And then it'll say something like, with 0 milliliters sodium hydroxide, let's say that's A. B would be with 10 milliliters sodium hydroxide. C would be with 50 milliliters sodium hydroxide, et cetera, et cetera, et cetera. And so if we're looking at an actual problem here, let me grab one real quick. We could say like, well, let me finish my kind of train of thought here. So so each of these things is going to take you to a different part of the pH curve. And on this pH curve, we don't know exactly where that is because I haven't told you what the acid is or what any of the concentrations of sodium hydroxide are. But it'll take you to somewhere on this pH curve. And where it takes you determines where it takes you on the pH curve has a different problem solving strategy. So if you're here on the pH curve where you haven't added any hydroxide, the way that you solve the problem is going to be different than when you're here versus if you're here versus if you're here. And so there's really 4 different possible calculations you can do for a titration problem depending on where you land on the pH curve. So these, unlike a normal problem where it says like, or unlike maybe the problems you're familiar with where it'll be, the problem is sort of limited in the way that you can work it. You have like one set of, you have one set of like a problem solving strategy, and you just always use that problem solving strategy. Here, you kind of have to do a little bit of work up front to figure out exactly what problem solving strategy you're going to use. And so earlier on, I think I've been saying this for a while now, one of the reasons this doesn't lend itself particularly well to just plugging in values is that it takes a little bit of chemical intuition and practice, which is why I've been encouraging you guys to, I can change this to make it, the pH will always be greater than 7. But it doesn't necessarily have to be 8. Yeah. But yeah, so you have to kind of figure out where you are. So let's take a look at some specific example here. So we'll probably get to the polyprotic stuff on Monday. That stuff isn't as bad as maybe it looks. I don't know. It's semi-quantitative. It's a little bit more qualitative in terms of how you do the analysis, so it's not as bad. At least the stuff we'll do. But let's take a look at this titration stuff real quick. So let's say you have 50 milliliters of 0.10 molar acetic acid. That has an association constant of 1.8 times 10 to the minus 5th. And you could say it's titrated with 0.10 molar sodium hydroxide. So there's a bunch of different places that we can kind of look at here before. So if we're here, if we're on this pH curve, right? At this point on the pH curve, where we haven't added any sodium hydroxide, all you really have there is just a weak acid problem. So it's 0 milliliters of sodium hydroxide. The question could be rephrased as 0 milliliters of sodium hydroxide. The question could be rephrased as what's the pH of a solution or like, yeah, what's the pH of 50 milliliters of 0.10 molar acetic acid. So that's just a weak acid problem, right? You set up a Rice table. There's nothing really fancy about that. The fact that you have 50 milliliters doesn't really matter. The pH is going to be the same regardless. So you're really just calculating the pH of a 0.1 molar solution of acetic acid. So that's at this point. When we start adding in acid, so let's say you have some, or sorry, when you start adding in base, when you add some base, which are before the equivalence point, these end up just being buffer problems. And so you want to use pH is equal to the pKa plus the log of A minus over HA. So that's for this part. How many different colors I can use here? It's yellow. And then when you're at the equivalence point, so when I'm right here, whatever that ends up being, let's see, there I'm just doing a weak acid, strong base. So we have a there you're looking at the pH of a weak base salt. So it, whatever A minus is going to dictate what the pH is.
How did you know that 50 milliliters was the equivalence point?
Oh yeah, sorry, I'm not actually sure what the equivalence point is up here. Hold on. Let's just simplify this by it increasing volumes of sodium hydroxide. That's just me not being consistent. So all I'm saying up here, all I was trying to point out up here is that the pH at increasing volumes of sodium hydroxide, that's the general question. And so I was giving some examples of what the volumes could be. And then I accidentally just used the same lettering system down here. So yeah, the equivalence point is not necessarily 50 milliliters. We have to figure out what that is.
Is the halfway point to the equivalence when there's like equal moles, right?
That's right.
The
so
acid in the...
yeah, okay. And that is still falls into this region here. So halfway to the equivalence point is when A minus and HA are exactly equal. So you still use this equation, but this term just kind of disappears. So whenever you have, so the way that I know that to use this is that I have some of the weak acid there, but I also have some of its conjugate base left. And so I know I have a buffer there. We'll come back and look at that. I won't be able to work through every single one of these, but we can look at some of them before the end. And then once you get past the equivalence point, So here your pH is dictated, I don't know how to say that concisely. pH is just the pH of the concentration for the strong base. So you'd look at like the sodium hydroxide concentration, recognize that that's equal to the hydroxide concentration, and then eventually convert that into pH. So you calculate like the PaOH, and then calculate the pH from that. But it's just dominated by the sodium hydroxide concentration. So it just becomes like a problem where the question is, you know, what's the pH of a sodium hydroxide solution with that's, you know, 0.1 molar or something. That's the entirety of the problem. So the calculation is really easy. So, you know, it's like negative log of OH minus, and that gives you the POH. And then you can calculate the pH by saying it's 14 minus the POH. But just the general idea here is that here at the top, sodium hydroxide dominates. Here, A minus is the dominant species. Here it's HA and A minus. And then at this point, it's HA. And so there's like, you know, there's two different ways to kind of look at this. One is, if you just want to get good at solving the problems, you can sort of develop some sort of workflow around this idea here. Like what part of the pH, which part of the titration curve do I want to use which problem solving method? But once you kind of get that down, you can go back and sort of understand like why that's true. You know, why do we use a buffer formula at this point? And like, why can't we use, the question you could ask yourself is like, why isn't that valid up here? Or why can't I use the Henderson-Hasselbach equation here or at the equivalence point? So sometimes it's like, if you can't answer like why you should use something, you could ask yourself like, why not use a different problem solving strategy? And that'll sometimes shed some light on like understanding the problem in a more firm way. All right, so let's look at like a particular situation here. So let's look in the buffer zone. So if we just had some acid in, sorry, some base in, then we can let's say that we add we could say, what's the pH after 10 milliliters of sodium hydroxide is added? So, you know, how do you know where you are in the pH curve is sort of the general question here. Since you have a problem solving strategy for different parts of it, you need to know where you are on it. And you don't necessarily need the pH curve to figure that out. The starting point generally is to write out your chemical reaction. So I have acetic acid. So you want to write out, let's say, you want to write out the neutralization reaction. So the neutralization reaction tells you where you are in the pH curve. So if we look at this, We just want to track the stoichiometry here. So when you're working in the neutralization reactions, remember that we always want to work in moles. And so you want to very quickly, let me find my calculator here. You want to very quickly convert everything over to moles. So if you've got 50 milliliters of 0.1 molar acetic acid, so I can take this part here. This is 0.005 moles of acid. So that's how much I'm starting with. That's not going to change. Well, I shouldn't say that's not going to change. That's not what we're varying here. We're changing the concentration of strong base by kind of adding it incrementally. So you're always titrating 0.005 moles, I guess is what I'm saying. But the number of moles of sodium hydroxide that you're adding will change. How much sodium hydroxide do I have? That I just need to take this 10 mils here and multiply it times the 0.10. So we calculate the moles from the concentrations and the volumes. Hopefully that's not too challenging at this point. All right, then we want to figure out, I'm not sure exactly what the best bookkeeping method is here. I hate to put rice just because I feel like it implies that you're doing an equilibrium calculation. But we can look at it. I think maybe it makes sense to look at it through this. So remember, I'm just using the rice table here as a bookkeeping, the AC before after change. Before after change. I like that. Thank you. Call it ICF, initial change, final change, final, initial change. Any of those are fine. Something to indicate, I guess, that it's not. I'll do B. C, E, A, just because at least it looks radically different from rice. ICF is fine too. These are not like standardized across the entire field of chemistry. It's just, it's a way to keep track of what's happening in the reaction. So it sort of just depends on who's teaching it. I don't even think my chemistry instructor even taught us this. So, or even like a method for keeping track of things. It was just kind of like, hey, figure this out. And then you just went home and cried for a while until you figured it out. All right, so before is 0.005 moles. Then we want to see what the change is. So the change is going to be whatever the smaller number is. And you don't have to write moles over here. In fact, I'll just remove that. But the change is going to be whatever the smaller number is going to be, it is typically. So the acid and the base react. At the end of the reaction, you have no more sodium hydroxide left over. And the amount of acid that you have is going to be reduced by whatever amount of sodium hydroxide you added. So you've neutralized this much of the acid. And so at the end of the reaction, you have 0.004 moles of this. The change over here, and zero this. The change over here, we started with none of this. We don't care about water. Whatever amount of acetic acid that gets neutralized is going to get neutralized and become the salt, the weak base salt over here. And so that ends up being 0.001. Okay, so at this point, like once you're done with the neutralization, you want to back out everything back into concentration. So here we're working in moles. That's only for the neutralization reaction. pH, remember, is a measure of concentration, so you have to divide by the volume to figure that out. And so how do I know this is a buffer? Well, I can use my Henderson-Hasselbach equation, that pH equals the pKa thing. Whenever I have HA, and I'll use, I don't know, bright pink maybe for A minus. and its conjugate base. So this is HA and this is A minus over here. And so now I recognize that I need to use this. And you'll note that the Henderson-Hasselbach equation calls for concentration. So those brackets, remember, mean concentration. So if you plug in the mole ratio, I don't know, maybe you'll get the right answer since you're just dealing with ratios, but it's always a good idea to back out into concentration. So what's our total concentration going to be? It's going to be these numbers, concentration of each of these, is going to be the number of moles divided by whatever the total volume is. And so if we look back up in our problem, we started out with 50 milliliters in our beaker. So I've got 50 milliliters in this beaker over here. And then I'm adding in stuff from my burette. And so how much I add is indicated in the problem. It says, okay, I added 10 mils. So this is the addition of 10 mils over here. And so my final concentrations are just going to be 60 mils. Or my final volume is just going to be 60 milliliters. So A minus is just going to equal 0.001 divided by 60 times 10 to the minus 3. And HA is going to equal 0.004 divided by 60 times 10 to the minus 3. So for these problems, if you forget to back out of the concentration, it's not the end of the world, because these units, this ends up canceling out since they share the same volume. But it's a good idea to just get in that habit at the end of the problem to convert back into concentrations, unless you really understand what you're doing. I would just always convert to concentration at the end of the problem. But yeah, so then we can just calculate this very quickly. We can say, okay, well, the pH is going to be equal to the negative log of the Ka value, which is 1.8 times 10 to the minus 5th, plus the log of these concentrations over here, which come out to be 1 to 4. So you can see why it doesn't matter that I convert back to concentration or not. And then so ultimately, we come out with a pH that's equal to 4.14. So the crucial thing here is, punching through the numbers here and sort of plugging in values is fine, but you have to know like what the workflow is going to be for the problem. And so the crucial thing here is that once you write out the neutralization for the reaction, if I'm at the point on the pH curve where I have some of this present and some of this present, so some of the HA and A minus, that's when I know that the Henderson-Hasselbach equation is what I want to pull out. That's the indicator for what's happening in the reaction. If you feel like you understand what's going on in terms of practicing for the exam, I would go through random problems. Some of those problems may not be something to like. There's so many problems on there. I doubt some of those, the more weird ones, are going to be things we covered. So don't beat your head up against the wall. If you get stuck on one, post it on Piazza, and me or Ryan will answer about whether or not you have to worry about it. You don't have to know the various indicator colors. We'll talk about indicators on Monday, but you don't have to know you don't have to memorize the colors or anything. But you will have to be able to like. Let's just save the indicator stuff for Monday. But yeah, you will have to know about like, I think on the homework, it's like, oh, I've got a color where one's blue and one's green or whatever, or one's blue and one's yellow. What's the color of this solution at a particular pH? Yeah, you should know how to do that. Come out on test. I don't know what that means. The indicator stuff? Yeah, you probably have, yeah, you'll probably have an indicator. Well, you have some sort of problem related to that. The important part about the indicator is not the thing that we care about is not necessarily like saying what color it is. It's being able to look at a structure. What you want to be able to do is look at a structure like something like this. Sorry, shorthand. In case you don't know that. And say like, at pH 1, pH 5, pH 8, pH, I don't know, 12. What's the protonation state? And actually, let me make this simpler, so we don't necessarily need that over here. I don't know, maybe there's a need to put more than one on there. So you can do this, you can figure out what the protonation state is by just doing like a rogue titration polymer. Yeah, you should get that titration homework stuff due by Sunday. Did I not put an assignment date on there, or are you just asking because I changed stuff?
The thing about that, it has some about polyprotic and solubility in that homework, and you took down the LEs for those.
Damn, the solubility stuff, I forgot that it's on there. Yeah, maybe I'll make that optional, so you at least have the problems available for the stuff that's not solubility oriented. Thanks for bringing that to my attention. I'll make an announcement about that immediately after class.
So that one won't be graded?
Yeah,
that
probably not before
homework.
this exam, yeah. It'll be optional or something, just because it has solubility stuff on it. I don't know. I guess some people probably have already done it, but I'll figure out something. Let me think about it after class. Yeah, if you don't feel solid on everything, I definitely wouldn't just start working random problems. You want to take sort of a systematic approach. I put those problem-solving videos up. I think, even though the way we ask stuff is different, and like obviously there's always some nuance or something, it kind of goes through the broad ideas of acid-base chemistry. So it gives you a handle on every type of problem you might encounter. So if you can kind of work through all those, that's sort of and understand what's going on, then you can move on to working on titrations and doing random problems. But yeah, you have to start out. Let's see, what would I recommend? I definitely would not just jump into doing random problems. You're going to get quickly overwhelmed. But also, if you're just kind of getting started studying, make sure that you parse your time appropriately. You don't want to spend, it's easy to kind of get lost in the details on this stuff. You don't want to spend like a whole day, like 12 hours just kind of playing around with pH for strong acids or something, because you got to move on. So, but yeah, before you kind of move on, you want a foundation. Yeah, videos are good, I think. You need a good foundation in understanding the pH. The starting point is like, I would say before you kind of get just jumping around in the problems, the starting point is like understanding how to calculate pH for strong acids. And then be able to like calculate, and then like understanding neutralization reactions. The buffer stuff is in there somewhere as well. Yeah, maybe buffers. But the buffer stuff shouldn't be too hard. It's really just those are the easiest calculations to do. But these three things are kind of like the foundation for all of the rest of the stuff. So you can't really do titrations until you really understand these three types of problems. And titrations are sort of the harder ones, I think. But so if you can understand these, then I think you're ready to kind of jump into doing random problems, and then you start discovering like it's impossible to cover everything in class or work out every type of problem. You start discovering like weird one-off problems that don't really make sense, and those are exceptions or things that are kind of outside of what you understand, and then you can work through those. Yeah.
For the above question, would the answer be pH equals 5?
Up here? For this one?
And below that, where what's the protonation state of the acid?
Oh, yeah. This is acetic acid. So the pH. Well, it's asking what the protonation state is. So that's asking at pH 1. Is this proton here on or off of the molecule? So pH 1. It's asking what state the molecule is, and is it like this? Or is it like this? You want to think of this as being like a basic part of the molecule. And so at pH 1, it's all going to be in the red state. Let's see, at pH 5, yeah, then you're going to start to see, maybe there it's where it becomes basic, which I think is what you're saying. And then after that, it's just always basic, like it's always deprotonated. Once you get above the pK of the acid, the thing is pretty much deprotonated. But yeah, generally the hardest part of this test, in my opinion, I mean, there's a lot of things that are hard about it, but the hardest thing for students is like knowing what you're looking at, like in terms of problem solving setup for a particular problem. So working a lot of random problems is ultimately where you need to be, because you need to be able to identify what kind of problem you're working on, if that makes sense. So, you read a problem, they all kind of sound the same. It'll say like, I've got a certain concentration of acid, I got a certain concentration of base. And so you need to figure out like, what am I dealing with here? Is this a buffer? Is this a weak acid problem? Is this a weak base problem? Is this a basic salt, an acidic salt, etc.? And trying to figure out what type of problem it is can be hard. And I think the GChem website is like particularly well built out around the acid-base stuff, because we know students have problems with this. So that's a really good resource to have. But yeah, that's my advice for the exam. I think at this point, it's kind of, I don't know how I would study for a weekend in this exam. I feel like I tried to do that when I was an undergraduate, and I ended up failing the test. Not to discourage you, but maybe I tried to cram for it all in one day. I know that doesn't work for sure. So if you've got the whole weekend and you've got all of next week, you might be able to pull out a win if you have enough time to study for it. But you're definitely behind at this point. Okay. Let me think about what to do with that homework, and I'll make an announcement, and I will see you guys on Monday. Have a nice weekend, and I hope your studying and stuff goes well.
Have a good day.
Yeah, bye.
Thank you.